Okay, welcome. Now, today we will discuss some exercises which I have left during the discussion. And before going to do exercises, I would like to recall some definitions which we have mentioned. So, as you know that we have already mentioned that a family of open subsets of X, so O be a family of open subsets of X, and a subfamily of this family of open sets is said to be base or basis of F if every open set G in O is the union of members of B. Okay, if this family B is countable, then we say that the O has a countable base for O, and we have proved the characterization which we will use. If O, let O be the family of all open subsets of a metric space X, then a subfamily O is base for O if and only if every point X belonging to an open set there exists Bx, an element in the B such that X is in Bx and Bx is a subset of O. So that was the characterization of the base or countable base, and we have seen several examples base, countable base, and we gave the definition of a second countable space. So a metric space X is said to be second countable space if there exists a countable base for the family of open sets. And we have already seen several examples for this. And a metric space X is said to be first countable, okay, or first axiom space if every point X in X there exists a countable family. This is countable family of open sets containing X such that every open set G containing X also contains a member of this one. That is to say, B and X is a subset of G for some N. Okay, then we have seen several examples of first countable space as well as for second countable space, and we have proved that every metric space is a first countable space. Okay, and then let us take here is the exercise. So first we have this exercise. So let XD be a metric space. Okay, and Y be a non-empty subset of X. If XD is second countable, then prove that YDY is also second countable. In other words, if a metric space is second countable, then the subspace of this countable second countable space is also second countable. So again you will have to prove that second countable space, so you have to prove that it has a countable base. So you have to prove that this Y dy has a countable base. Okay, so now here the only thing is that keep in mind XD is a second countable space. So the metric space D is second countable. It means that every family of open set, okay, has a countable base. Okay, countable base for open sets in X. So here we have to prove that the family of open sets in Y has a countable base in Y. So that is the only thing to prove. So let us take B is equal to B is a family of open sets Bn. Okay, so this is countable base for the family O of all open subsets of X. So O is the family of all open subsets in X. Keep in mind, and Bn is a countable base. Okay, in X. Then we can see that the B star. Okay, B star is equal to Bn intersection Y. So because Bn is open in O, So, and y is a subset of x, or not y, dy is a subspace of y, then from Bn we can get the open balls or open sets, okay, with respect to Bn. So, what is this Bn intersection y? This is open in y. So, and of course, this is countable. So, B star is equal to, is the family of Bn intersection y is countable. Okay, and now we claim that this B is nothing but it is the base for the family of, for the family G of open sets in Y. Okay, so here is the only thing is you have to be very careful about whether a set is open in X and open in Y. So let us take, because we want to prove that this family is, of course this family is countable, so we will have to prove that this is a base for the family of open sets in Y. So let us take G, okay, let G be an open set in Y, and let X is any element in G. Then we will have to prove that there is an open set containing X contained in G. This we have to prove. So, because X is in G, then there exists, G is open set in Y, then there exists an open set O in X. Because G is open in Y, so corresponding to this G, there exists an open set O in X such that G can be written as O intersection Y. This we have already proved. Okay, so this you have to keep in mind. And also, you see that X is in O intersection Y. Okay, why? Because X is in G. So X is in G, so X is also in O intersection Y. That is to say, X is in O and X is in Y. So X is in O and X is in Y. Now O is what? O is an open set. So O is in capital O. Okay. So corresponding to this O, there exists a B and not. Okay, in B such that X belongs to this B and not, and B and not is a subset of O. And now since Y, X is in Y, from here X is in Y, we have X is in, so you take X is in B and not intersection Y, and here this is also a subset of O intersection Y, but O intersection Y what? It is equal to G. Okay, so we have, but this is what? This is your an element of B star from here. So it is an element of B star. So we have proved, so we have taken an element in G and we have proved that there exists an open set B and not in Y in the family open sets of Y, okay, containing X and contained in G, and therefore B star forms a base for G and hence Y dy is second countable. So this way we can prove that so you will have, whenever you do any exercise, try to use the results which we have already proved and the definition. So or sometimes we have to prove the characterization, because here we are using the characterization of the base. We are not using the definition which we have given. We are using the characterization. So you have to do it this one. Now the second exercise is that let XD be a metric space and Y be a non-empty subset of X. Now if XD is first countable, is so Y dy, justify your answer. See, here is we have proved that a subspace of a second countable space is second countable. What about the first countable? Can we say that a subspace of a first countable space is first countable? Give the answer, and justify your answer. So this I left for your exercise. Okay. Then the third exercise is the following. Let X is equal to R2 with the usual metric space. Okay, and X is an element in capital X whose components are x1, x2. Be arbitrary element, and G lambda X is the ball. G lambda X is the set of all points Y such that y1 minus x1 square plus 3 times y2 minus x2 square is less than lambda. It means that it is the disk. Okay, this is the disk. So we have this disk, and now where lambda is greater than 0, then prove that the family, this family, okay, for each x in X is a base for the family of all open subsets of X. So we prove that this is nothing but this family of G lambda X is a family or is a base for all open subsets of X. So it's again very simple, and we can see that the proof very easily. So again we will use the characterization, and that's why I gave the characterization first. So let G be an open set in X and X is in G. Okay. So G be any open set in X and X is in G. So what we will have to? We will have to find an open set. Okay, an open set in this family containing X and contained in G. This we have to find. So because G is open and X is in G, so X must be a center of some open sphere contained in it. Okay, so there exists R greater than 0 such that SRX is the subset of G. Okay, now we know that SRX is equal to set of all points Y such that this y1 minus y2 whole square plus y1 minus x1 square plus y2 minus x2 square is less than epsilon. Okay, this is the open ball with the usual metric. So this is the open ball with the usual metric. Now let lambda is equal to r square. So if we take lambda is equal to r square, then if y is in G lambda X, any G lambda X, okay, so lambda is equal to r square, then we will see that y satisfy this condition. Okay, so this because y lambda, so here is equal to y1 minus x1 square plus lambda is equal to, so this is 3 times y2 minus lambda 2 square minus less than lambda, which implies that y1 minus x1 square plus y2 minus x2 square is less than lambda, which is equal to r square. Okay, this means what? This means that y belongs to the open ball with center X and radius r, and so y belongs to the G lambda X, and G lambda X is a subset of this set, and this set is a subset of G, and hence this family of open sets is a base. This collection or open set is a base for all open subsets of X. So this is the way to prove the exercises. So again, what we have done, we just proved this result by using the characterization of a base. So whenever you are proving any result, keep in your mind the definition of both the things. So keep two things you have to check. First, what is given? Okay, whenever you are trying to prove a theorem or an exercise, you will have to see that what is given or what are given. Number one. Number two, what you will have to achieve. What do you want to prove? Okay, this one. And then the third one is that how can we achieve our goal by using the things which are given. Can we use some kind of the characterization, or we can use direct definition or some results? So these are the basic things, and then we can get the result. Okay, so then after that we have discussed the dense set. Dense set means that a set A in a metric space X is dense if the closure of A is equal to X. And here we have proved that the characterization of the dense set. So a set A is a dense set if and only if the distance from any point X to A is equal to 0. The distance from any point A to A, the distance from any point in X to A is equal to 0, and it is equivalent to say that A has non-empty intersection with every non-empty open subsets of X. It has non-empty intersection with every non-empty open subset of X. In other words, if O is an open set in X, then A intersection O is non-empty. Okay, so this is the characterization which we have already proved, and then we have seen several examples here. This we have already completed, and then we have seen that PAB, the set of all polynomials with rational coefficients, is dense in CAB. So keep all these things in your mind. And then we have proved this result. If Gn be a sequence of dense open sets in a metric space X, then the intersection is also dense. Keep in mind here is, I have already mentioned that Gn is a sequence of dense open sets. Okay, so this is a dense open set, then the intersection is also dense. This we have already proved. So, and then the separable metric space. So a metric space X is separable if it has a countable dense set. If it has a countable dense set, and we have given that R is separable because Q is dense in R and it is countable, so it has a countable dense set. C is separable because this set is dense. Rn is separable because this is a countable dense set in A. This we have already proved. LP space. LP space is dense as we have seen that this set A is countable and dense in LP space, and CAB is separable as PAB with rational coefficient is countable dense set in X. Okay, so a discrete metric space X is separable. Now a discrete metric space X is separable if and only if X is countable. Okay, because the closure of X it is self. So here is LP space. So LP space is not separable. This we have already proved. So I am not going to give the definition of this one. And we have seen that if X is separable, then the subspace of X is also separable. Okay, as we have seen that for the previous case, second countable space. Okay, and so if X is separable, then the subspace of X is also separable, and we have already proved that a metric space XD is separable if and only if it is second countable. So this is very important thing to prove that is separable. Just you prove it is the second countable, and to prove the second countability, you may prove separability. So a metric space X is separable if and only if it is second countable, and it can be asked also as a MCQ. Okay, so then here we have some exercises. Okay, so let me take the exercise this one. So here is you have S is a set of points n plus m under root 2, where m and n are integers. So S is the set of points m plus n plus m under root 2, where m and n are integers, and a be any real numbers, such that a is less than, strictly less than b. Then prove that there exists an element s, small s, in this set such that a is less than s is less than b. Okay, what does it mean? So because A is less than B, A is any two number. So meaning is that if you choose any two real numbers, okay, you can find another number from this set in between A and B. This is a very important thing. So it means what? It means that this set is nothing but it is dense in R. So the set S, so prove that this set S is dense in R. So it can be asked in several ways. The first way is that prove that the set S is dense in R. The second way is that only prove that there exists an element S in X such that S lies between A and B. So there are two ways to prove that. So let us prove it. So prove this one. It is not so easy. I think you will have to think a little bit more about it. So suppose if x, y are two elements in X and K is an integer, okay, then x plus minus y and kx is also in S. Okay. Why it is so? You can see that here is this is the set of all n plus m under root 2. Okay, so because S and S are in this set, so S plus minus S also in this set. And if you multiply by k, okay, this, okay, any number, then it is also in this set. Okay, so this is very obvious to say that x plus minus y and kx also in S. Now let nm, okay, so nm we are defining as m square root m, that is the greatest integer less than or equal to this is the greatest integer function. Okay, so nm is equal to the greatest integer less than or equal to m under root 2. Keep in mind this is greatest integer. Okay, then we can see that the m under root 2 minus nm minus nm, keep in mind minus nm is equal to greatest integer function, this is less than 1. So this is greater than 0 and less than 1. And it is easy to see that if n plus m under root 2 is equal to n prime plus m prime under root 2, then n prime must be equal to n and m prime must be equal to m. So this we can see that. So let sm is equal to m under root 2, okay, divides n m, okay, m. So let's take this is equal to m and divides n m. Then we see that 0 is less than sm is less than 1 and sm is in S. And also if m is not equal to m prime, then sm cannot be equal to sm prime. And hence we conclude that sm for all m is prime, m is an integer. This is an infinite subset of S intersection close interval 0 open interval 1. Now given epsilon positive, we partition this interval close interval 0 open interval 1 into k equal parts so that each subinterval has length less than epsilon. At least one of these subintervals must contain two distinct elements, say sm prime, okay, of S intersection close interval 0 open interval 1. Without loss of generality, we may assume that Sm is less than Sm prime. Then we have 0 is less than Sm prime minus Sm and it is less than epsilon. And so now since Sm prime minus Sm lies in S, we have shown that given epsilon positive there exists an element small s in capital X such that 0 is less than S is less than epsilon. Now, let epsilon is greater than 0, then such that B minus A is greater than epsilon. Okay, because here we are assuming that A is less than B. So, we are taking B minus A is greater than epsilon. Okay, then there exists an element, there exists an integer n such that A is less than n epsilon is less than B. For choosing n to be the least integer n such that k epsilon is greater than A, then n minus 1 epsilon is less than or equal to A is less than n epsilon. So, we claim that n epsilon is less than B. For otherwise a contradiction. Now, we take epsilon is equal to B divides A divided by 2. Okay, then there exists S in S such that 0 is less than S is less than epsilon. Hence, there exists an integer n such that A is less than ns is less than B. Since ns in S, the result is proved. So, we can prove in this way. This way is we can prove that this set is a dense set in R. Okay. So, now I stop over here and we will continue several other exercises in my next talk. So, thank you very much.